Okay, here's a few buffer problems. What's the pH of a solution after 10 mils of 0.1 molar sodium hydroxide is reacted with big excess? 50 mils of 0.1 molar HCl. We'll solve it by filling in the blanks. I'm noticing that since we have a strong acid, HCl, and a strong base, sodium hydroxide, it's not a buffer problem. It's simply a partial titration of a strong acid with a strong base, leaving a lot of strong acid remaining. We started with 0.005 moles of H plus. You get that by liters times moles per liter. And we have 0.001 or 1 millimole of the hydroxide. In other words, initially we had 0.01 liters at 0.1 mole per liter. That's 0.001 moles. And when the reaction's over, well, 0.001 will react, leaving us with 0.004. So there will be, it should show up, yeah, 0.004 moles remaining of the H plus, no hydroxide because it all reacted, and some water, but who cares because it's not going to change anything. We have 0.001 moles of water. You know, since the reaction's making water, that'll affect the volume of the solution. Isn't that interesting? Since the final volume of the solution after the reaction is over is 0.06 liters, you know, it's a solution, right? You can't change the volume of the solution. So no matter what's going on, we have 0.06 liters of solution. We don't care how much of that is water. So the concentration of H plus will be, if you do the math, moles per liter, you have a 0.0667 molar solution. The pH is the negative log of that, which is 1.176. That's the answer to question 11. Number 12, calculate the pH and the titration of 25 mils of 0.1 molar acetic acid by some sodium hydroxide after how much? Well, you've added 10 mils of the 0.1 molar. That will all react to make sodium acetate, leaving you with the 15 mils of acetic acid unreacted, and they give you the Ka of it. We need to find out the pH. So let's just, it's kind of like a limiting reactant problem. We'll see what's in the flask when everything's done, and we will then calculate the pH based on that using the Henderson-Hasselbalch equation. Initially, we have 0.0025 moles of acetic acid. Convince yourself that's true. 0.025 liters at 0.1 mole per liter. We also have 0.001 moles of hydroxide by a similar analysis, and nothing because the reaction hasn't started yet. All of that hydroxide will react, leaving us with 0.0015 moles of acetic acid. And all the hydroxide is now gone, and therefore the acetic acid acetate will result from that reaction going up by the same amount. There's your amounts when you're done. This is your acid. That's your HA. That's your conjugate base, and the Henderson-Hasselbalch, that goes on top. So the pH is the pK plus the log of this over that, so 4.74 plus 0.001 over 0.0015, which you should see all down there. See if I can X this out. There it is, giving us a final pH of 4.57. Take a good look at all that. And there you go. And question number 13. Looks like, look at this. I did not solve it by the Henderson-Hasselbalch, but you heard me say it out loud. You should get the same answer. Question 13, calculate the pH and the titration of 25 mils of 0.1 molar acetic acid using sodium hydroxide. Is this the same question? 10, 25, look, it's different amounts. 25 mils of acetic acid, 25 mils of sodium hydroxide. That's going to react completely. 25. When you're done, you're just going to have acetate, right? And so we just have to take the acetate. We'll have the pKa. We could just turn that into a pH. We also have the pKb. From that, we can get the Kb, and from that we can get hydroxide. From that we can get pH. So here's how we do it. The slow method is to just figure out what's in a solution when you're done. All of this stuff reacts, and so you just have acetate when you're done. So you end up with a flask that contains nothing except sodium acetate, and then we can just get the pH, which you can do by Ka equals x squared over the 0.0025, I think it is, 0.05. Therefore, x is the concentration of your hydroxide. The pH is 14 minus that. We get 8.72. Here's a much faster method to do it. You're going to get 0.0025 moles of acetate in 50 mils of solution. That's 0.05 liters, so it's 0.05 moles per liter, right? Is the concentration of acetate. I wonder if you could now solve. You can't really solve this by the Henderson-Hasselbalch, I don't think, right? All you have is acetate. You don't have any HA, right? So we can take that Kb, which is literally means the concentrated of the products over the reactants, solve for X. X is just done like the same thing down there, and the pH is 8.72. That is 11, 12, and 13.